In March of 1941, inside the submarine assembly bay at Mare Island Naval Shipyard in Vallejo, California, the faint glow of a welding torch cut through the dimness. Edward Nelson, a welder earning $11 a day, scribbled his irritation into a battered notebook. There has to be a smarter method. This is insanity, he thought. Navy overseers repeatedly urged him to speed up, but refused to consider the improvement he had already worked out. Navigating the tangled network of scaffolding beneath the unfinished wooden deck of a submarine, Nelson had just seen something that made his anger rise. An entire team of workers had spent a full shift installing just one small portion of deck planking. Massive support structures crowded the compartments below, where men squeezed into tight corners, tools in hand, fastening nuts onto bolts pushed down from above. Hours of exhausting effort were consumed simply attaching wooden boards to steel frames. This old-fashioned technique demanded accuracy, patience, and, above all, time. Time the United States could not afford as dark signs of war gathered across the Pacific. Yet here, in what was quickly becoming one of the busiest shipyards in the nation, construction procedures hadn't changed in decades. Theodore Edward Nelson, a 36-year-old California native, had gained his technical skill through years of hands-on experience, 15 years in machine shops throughout the state. 15 years understanding metal, electricity, and problem-solving, skills he knew could speed up their work, if only someone would listen. The Navy foreman had no idea that this irritated welder had already engineered the solution they needed. And Nelson himself had no clue that his simple idea, dismissed outright by his superiors, would soon save the U.S. Navy more than 50 million labor hours and permanently transform how ships were built. This turning point had actually begun weeks earlier, deep inside the tight compartments below deck, where the daily struggle against wasted effort was quietly being fought. The day was March 15, 1941, 8 months and 22 days before the attack on Pearl Harbor. Spread across 635 acres beside the Napa River in Vallejo, California, Mare Island Naval Shipyard sat 25 miles northeast of San Francisco. Established in 1854 by Commander David Glasgow Farragut, it was the first U.S. naval base on the Pacific coast. By early 1941, Mare Island had grown into the leading submarine building center of the West Coast. Production ran nonstop, 3 shifts a day, 7 days a week. With tensions rising between the United States and Japan, submarine construction surged dramatically. At the start of 1941, the shipyard employed roughly 12,000 civilian laborers, a workforce that would expand to nearly 50,000 by the year 1944. Among those initial workers was Ted Nelson, listed as employee number 3872. He earned $11 per day, serving on the daytime crew from 7 in the morning until 4 in the afternoon. His specialty was welding, mostly on submarine outer hulls and their internal components. Nelson was skilled, quick, and accurate, yet he grew increasingly upset by the wasteful, slow procedures he witnessed daily. The issue seemed to exist everywhere he turned, especially in the installation of wooden deck planks on submarines, destroyers, and aircraft carriers. The Navy required wooden decking for several practical reasons. Wood offered better grip than steel when wet. It was quieter for sailors walking on board. It also provided some insulation against the cold metal below, and if a fire occurred, wooden decking could be replaced or fixed far more easily than welded metal plates. But while wood had benefits, the method of installing it was outdated, overly demanding, and unbearably slow. The accepted approach, unchanged since World War I, involved a complicated sequence of tasks. Workers began by drilling holes into each wooden plank at carefully measured distances. These holes were then countersunk so the bolt heads would sit level with the surface. After that, the planks were placed onto the steel deck structure. What followed was the most exhausting stage. Crews had to assemble large scaffolding systems underneath the deck, inside the tight compartments of the ship or submarine. Several tiers of platforms were needed so workers could reach the underside of the steel framework. After building the scaffolding, teams both above and below the deck worked together to insert long threaded bolts downward through the planks and steel support holes. Below the deck, workers balancing on narrow platforms in dark, confined areas would twist nuts onto the exposed ends of the bolts. Using wrenches, they tightened the nuts, pulling the planks firmly against the steel below. Finally, workers on top filled each countersunk hole with a wooden plug, leaving the deck smooth and level. This entire procedure had to be repeated for every segment of decking. A submarine alone could require hundreds of square feet of wooden surface, meaning thousands of individual fastening points. An aircraft carrier needed even more, its wooden flight deck stretched across tens of thousands of square feet. The amount of labor required was overwhelming. Installing the deck on a standard submarine required a crew of 12 to 16 workers and took between 5 and 7 days to complete. Constructing the scaffolding alone consumed 2 full days, while taking it apart required yet another day. The remaining time was spent on inserting and tightening the bolts. Ted Nelson had carried out this job many times. He had spent countless hours standing on narrow platforms, forcing nuts onto bolts inside cramped submarine spaces that were barely 4 feet tall. His back throbbed from constant bending, his hands were marked with cuts from wrenches slipping, and his patience had completely worn thin. However, his irritation was not driven only by physical discomfort. He recognized the larger problem. A war was approaching, and everyone at Mare Island sensed it. The shipyard was already falling behind on submarine production. The Navy needed vessels out at sea, not stuck in dry dock waiting for deck planks to be installed. Each wasted day brought the country closer to a fight it was unprepared for. Nelson understood there had to be a faster method. For months he had been mentally working through the issue during slow welding shifts. To him, the solution seemed obvious. Rather than fastening bolts from the top and tightening nuts from below, why not weld mounting studs directly onto the steel frame? Weld them from one side only, from above. That would eliminate the need for scaffolding, remove all nuts and bolts, and prevent workers from having to squeeze into tight spaces beneath the deck. A quick, strong weld could do the job. The idea itself was simple. A threaded stud, essentially a bolt without a head, could be welded to the steel structure in a split second. The wood planks could then be secured using threaded inserts or special nuts designed to fit onto these welded studs. Everything would be done from the top side. No scaffolding, no below-deck labor, and no coordination between workers above and below. Nelson had seen stud welding before, though only in a restricted form. The technology already existed for welding studs onto flat, horizontal steel plates. In this method, a small amount of flux powder was placed on a flat metal surface, the stud was positioned on the flux, and an electric arc fused the stud in place. But this approach only worked on level surfaces. Flux powder would simply spill off if used on vertical or overhead surfaces, and shipbuilding required welding in every possible position, vertically, horizontally, overhead, and at varied angles. This limitation had baffled welding specialists for 2 decades. How could stud welding be adapted for surfaces that were not horizontal? Nelson believed he had finally solved it. The answer was so straightforward that he nearly laughed when he realized it. Instead of using loose flux powder, the flux could be sealed inside a tiny ceramic cap. The cap would fit over the end of the stud, holding the flux in place regardless of the welding angle. He immediately drew the idea in his notebook. His idea required a handheld welding tool equipped with a spring-loaded system to push the stud firmly against the metal surface, an electric trigger to ignite the arc, and a removable ceramic cap that contained the flux at the tip of each stud. The entire process would take less than a single second for every weld. One person could install many studs in the amount of time it currently took to complete just one bolted fastener. Nelson presented his concept to his immediate supervisor, a Navy lieutenant named Morrison. The discussion lasted under 5 minutes. Morrison barely glanced at the drawings. "We already have established procedures, Mr. Nelson. We follow Navy specifications. If you want to stick with welding instead of commenting on installation methods, continue doing the work assigned to you." Nelson refused to give up. He then brought the idea to the shipyard's top welding expert, a civilian engineer named Hartwell. Nelson described the reduction in labor, the savings in time, and the elimination of expensive scaffolding. Hartwell was kinder than Morrison, but just as uninterested. "Son, people far more knowledgeable than either of us have tried to solve this issue for 20 years. If the answer were that simple, someone would have discovered it already. Besides, the Navy has strict specifications. We can't just modify procedures because a welder has a suggestion. You'd need approval from the Bureau of Ships in Washington. You would need engineering analyses. You would need prototype testing. That can take years." "We don't have years," Nelson insisted. "We need submarines right now." Hartwell simply shrugged. "That isn't my responsibility, Mr. Nelson. My job is to build vessels according to approved standards. Your job is to weld what you're assigned to weld." Nelson walked away, angry and discouraged. He had presented a method that could save thousands of hours on every submarine, yet they dismissed him without true consideration, not because the idea lacked merit or wouldn't succeed, but because he was only a welder. Because changing procedures required paperwork and bureaucratic approval. Because innovation mattered less than preserving long-standing rules. He made one last effort and wrote a formal letter to the shipyard's commanding officer, Captain Thomas Withers. He wrote it carefully, laying out the inefficiencies in the current process, proposing the stud welding method, and estimating both time and cost savings. He submitted the letter through official channels, following the designated procedure for worker recommendations. 3 weeks later, he received a response. It was a form letter thanking him for wanting to improve shipyard productivity. It politely stated that all technical suggestions were reviewed by the Bureau of Ships Engineering Board. It noted that his proposal had been forwarded for evaluation. It concluded with a realistic reminder that the review typically required 18 to 24 months. He would only be contacted if his idea was selected for additional evaluation. 18 to 24 months, by that time, the work could already be finished or even lost. Nelson crushed the letter in his fist and tossed it into the trash. That night he made a decision that would reshape his future and ultimately influence naval development. If the Navy refused to listen, he would build the device himself. He would demonstrate that the concept worked, and once he proved its value, they would have no choice but to pay attention. He cleared out space in the small garage behind his modest house in Vallejo. His wife, Emma, watched anxiously as he gathered leftover metal pieces and welding tools. "Ted, you're going to lose your job," she cautioned. "You're supposed to work on Navy equipment, not invent your own tools." "This will help the Navy," he insisted. "They just don't realize it yet." For many weeks, working nights and weekends, Nelson created his first working model of a stud welding gun. The prototype was rough, but it operated. It had a pistol-style grip, a spring-loaded mechanism to hold and press the stud, an electric trigger linked to a welding power source, and a fast-loading system for inserting new studs. The most important breakthrough was the ceramic flux cap. Nelson experimented with multiple ceramic blends, various flux formulas, and different cap shapes. After many trials, he produced a cap that gripped the flux firmly, produced a clean arc, and could be made at low cost. By May 1941, he had a functioning device. He tested it on scrap metal in every position, flat, upright, overhead, and at angles. The tool worked without failure. Each stud could be welded in under 1 second. The resulting welds were stronger than traditional bolt attachments and, most importantly, required no work from below the surface. Nelson brought the device to the shipyard and showed it to other welders during their lunch break. They were amazed and enthusiastic. "This is going to save us a tremendous amount of time," one said. "You should show it to Morrison," another suggested. Nelson shook his head. "I already did." He wasn't interested. "Then quit and start your own company," a third co-worker advised. "Sell these guns to shipyards everywhere. You'll get rich." The thought had never crossed Nelson's mind. He was simply a welder, not an entrepreneur. He had no funding, no factory, and no knowledge of running a business. But the more he considered it, the clearer it became. If the Navy refused his invention, private shipyards might not. Kaiser Shipyards in Richmond needed workers. Bethlehem Steel in San Francisco was expanding. Shipyards along the Pacific coast faced the same production delays and labor shortages. On June 20, 1941, Ted Nelson turned in his resignation at Mare Island Naval Shipyard. His supervisor tried to convince him to stay. "Nelson, you're an excellent welder. Don't give up a secure job for a risky idea." But Nelson was resolute. "I'm going to manufacture welding guns," he told Morrison. "And when the Navy eventually comes back wanting to buy them, I hope you remember this conversation." He walked away from Mare Island carrying just $11, a garage filled with tools, and an unshakable belief that his creation would succeed. On July 1, 1941, he officially founded the Nelson Specialty Welding Equipment Corporation. To finance his new venture, he secured a $95,000 loan from the Reconstruction Finance Corporation, a government agency formed during the Great Depression to support small businesses. With that funding, he rented a modest workshop in Vallejo and began producing stud welding tools. The early months were harsh. He had no established customers, no name recognition, and no distribution system. He personally visited machine shops and small fabricators, demonstrating his device and describing the enormous time savings it could provide. Many people doubted him. A few were intrigued enough to test his equipment. Gradually, almost painfully slowly, orders started to arrive. By September 1941, he had managed to sell 18 welding guns along with several thousand studs equipped with ceramic flux caps. Then everything changed on December 7, 1941. Pearl Harbor. The surprise Japanese attack crippled or destroyed 8 battleships, 3 destroyers, 3 cruisers, and 188 aircraft. More than 2,400 Americans were killed. The United States was now at war. Shipbuilding was no longer just essential, it was a matter of survival. Within days, the shipbuilding industry exploded with desperate urgency. Kaiser shipyards began constructing Liberty ships at record speeds. Mare Island received emergency submarine orders. Bethlehem Steel and other private yards shifted into non-stop triple-shift production. And every one of these shipyards faced the same obstacle: they needed to build vessels faster. Traditional methods required too much time and too many workers, wasting hours America could not afford to lose. Suddenly, Ted Nelson's phone began to ring. Purchasing managers who had previously ignored him now urgently wanted his equipment. Kaiser shipyards requested 50 welding guns and 10,000 studs. Bethlehem Steel ordered 40 units. Even Mare Island Naval Shipyard, the very place that had dismissed him, requested 60 welding guns and 20,000 studs. His former supervisor, Morrison, processed the order. There was no apology, no admission that Nelson's idea had been right all along, just an official request demanding quick delivery. By January 1942, less than a month after Pearl Harbor, Nelson's small shop could no longer keep up with the flood of orders. Requests came in faster than he could produce his equipment. He needed a true manufacturing facility, more workers, and stronger machinery. He rented a larger plant in San Leandro, just south of Oakland. The building looked plain, sitting alone in a cornfield, but it offered space, electricity, and room to grow. By March 1942, he already had 20 employees. By June, the number increased to 50. By September, he reached 150 workers. The plant ran continuously, operating 24 hours a day, 7 days a week. Approximately 30 welding guns were produced daily, rolling steadily off the production line. The output of studs reached into the thousands per day. By this point, every major shipyard on the West Coast had adopted Nelson's stud welding technology, and the feedback they provided was remarkable. A submarine deck installation that once required a team of 12 workers and nearly a week to finish could now be completed by only 3 workers in a single day. By removing the need for scaffolding, 2 additional days of work were saved, and more laborers became available for other critical jobs. Not only was the work faster, but the resulting welds surpassed bolted joints in durability. In addition, wooden deck planks could be taken out and replaced more easily for repairs or routine maintenance. At the Mare Island Naval Shipyard, submarine production increased at an astonishing rate. Between 1941 and 1945, the yard completed 17 submarines, and the average construction time decreased steadily as improved methods were put into practice. While stud welding was not the only advancement contributing to these improvements, it became an essential part of the overall efficiency breakthrough. By the middle of 1942, the use of stud welding expanded beyond deck attachment and was being applied in numerous other ways, securing pipe supports, mounting equipment, fastening cable holders, and attaching bulkheads. Wherever a fastener needed to be fixed to a steel surface, stud welding offered a quicker alternative. The Navy Bureau of Ships, which had dismissed Nelson's ideas early on, began thoroughly examining his technology. Their engineering specialists investigated weld durability, strength, and possible failure points. Their findings supported what Nelson had always believed. His method didn't just save time, the welds it produced were stronger and more dependable than older fastening approaches. Then, on November 19, 1942, less than a year after he had walked away from his $11 per day welding job, Ted Nelson received a formal, unexpected visit at his San Leandro facility. 5 Navy officers in full dress uniform arrived without warning. Leading them was Captain Harrison, representing the Bureau of Ships. He addressed Nelson directly. "Mr. Nelson, we are here to inform you that the Navy has finished its assessment of your stud welding technique. We have determined that your invention has saved the United States Navy approximately 5 million labor hours in both submarine and surface vessel construction during the last 10 months. We expect that number to rise significantly as additional shipyards begin using your process." He paused before continuing. "On behalf of the Secretary of the Navy and the United States government, I am authorized to award you a citation for extraordinary service to the war effort." Nelson was speechless. The very people who had dismissed him, refused to consider his work, and pushed him into leaving his job to take a monumental risk were now honoring him. Captain Harrison seemed to recognize the conflict on Nelson's face. "I understand you submitted a proposal to Mare Island early in 1941, Mr. Nelson," he said. "I have reviewed that file. Your proposal was not given the proper evaluation at that time. That decision was incorrect, and I regret it on behalf of the Navy, the officer said. However, your choice to pursue and develop this technology on your own has allowed it to be implemented far more quickly than it would have through the ordinary government purchasing system. At times, the most patriotic action is to bypass official procedures and simply fix the problem directly. Nelson accepted the award with a mixture of emotions. He felt pride in what he had accomplished, satisfaction that his persistence had been justified, yet also irritation toward the bureaucratic system that had nearly stopped his invention from ever being used. The war continued to escalate, and production needs only grew. Nelson's company expanded once more, launching a second manufacturing plant in Camden, New Jersey, in March 1943. This new facility on the East Coast supplied shipyards in New York, Philadelphia, Norfolk, and Charleston. By the middle of 1943, the Nelson Specialty Welding Equipment Corporation had grown to more than 400 employees and reached annual earnings of roughly $4 million. Ted Nelson still worked 16-hour days on the factory floor, still wore the same tan shop worker uniform, and still took home only a modest wage of $1,000 per month. Every dollar of profit was poured back into growth, new machinery, and repaying loans. Yet the difference he made to the war effort could not truly be measured. The Navy's estimate of 5 million labor hours saved by late 1942 represented only the beginning. As the conflict continued and stud welding became routine in every area of shipbuilding, the labor savings multiplied at an astonishing rate. By 1943, stud welding was no longer limited to submarines. It was now used on aircraft carriers, battleships, cruisers, destroyers, and countless smaller ships. The Essex-class aircraft carriers, constructed by Newport News Shipbuilding and other yards, relied heavily on Nelson's stud welding method for attaching flight decks and interior components. Each carrier needed roughly 20,000 studs, and during the war, the Navy produced 24 Essex-class carriers. The Iowa-class battleships applied stud welding for deck planks, for mounting heavy equipment, and even for securing armor. The Baltimore-class heavy cruisers integrated the system extensively as well. Destroyer escorts, landing craft, patrol vessels, virtually every ship type gained from faster and stronger fastening techniques. However, the most profound transformation occurred in submarine building. Mare Island Naval Shipyard, the same facility where Nelson once worked and where his concept had been initially dismissed, became one of the world's most efficient submarine production sites. The shipyard completed 17 submarines over the course of the war and steadily improved its construction speed. Meanwhile, Portsmouth Naval Shipyard in New Hampshire emerged as the unmatched leader in submarine output, producing 79 submarines between July 1940 and July 1945. Portsmouth's remarkable results were achieved through several important innovations, but stud welding remained one of the fundamental technologies that made such performance possible. The shipyard adopted Nelson's technique on a massive scale, applying it not only for deck installation but throughout the entire submarine's interior structure. Its impact became clear through production records. On January 27, 1944, Portsmouth launched 3 submarines at once, the Redfish, Ronqual, and Razorback. That same day, a 4th vessel, the Scabbardfish, was also launched. For submarines launched within a single day, an accomplishment unmatched by any shipyard before or after. At its height, Portsmouth delivered 32 submarines in 1944, averaging roughly 1 submarine every 11 days. The Vallejo-class submarines, which represented the majority of wartime builds, took about 12 months from the moment their keel was laid to the moment they were commissioned at Portsmouth. This was months quicker than other facilities constructing the same models. Electric Boat Company, located in Groton, Connecticut, produced 74 submarines throughout the war. Manitowoc Shipbuilding in Wisconsin, although located far from the ocean on the Great Lakes, managed to build 28 submarines, which were then transported down the Mississippi River to the Gulf of Mexico. Altogether, American shipyards produced 203 submarines during World War II. Each submarine required thousands of stud-welded fasteners. Each stud saved valuable minutes of labor. When multiplied by thousands of studs on each submarine, and then multiplied again across hundreds of submarines, the cumulative time saved reached unimaginable levels. However, submarines represented only a fraction of the output. The real mass production came from surface ships and merchant vessels. The Liberty Ship program, overseen by the Maritime Commission and largely constructed at Kaiser shipyards, produced 2,710 cargo vessels during the war. Each Liberty ship needed approximately 5,000 to 8,000 stud-welded attachments for deckboards, cargo gear, weapons mounts, and ship fittings. The more advanced Victory ships followed similar standards. The scale of this shipbuilding effort was unlike anything ever seen on Earth. At the height of Liberty ship construction in 1943, American shipyards launched 3 vessels every single day, about 75 per month, and roughly 900 per year. Such output was possible only because of drastic changes in shipbuilding techniques, modular section fabrication, pre-assembled components, specialized labor roles, dedicated tooling, and faster fastening systems. Stud welding represented just one part of this transformation, but it was a vital part. Eliminating the need for scaffolding allowed workers to shift to other essential tasks. Rapid installation shortened assembly schedules. The strong, dependable welds ensured that these rapidly built ships could withstand fierce Atlantic storms and enemy threats. By the spring of 1943, the United States Navy formally recognized the influence of Nelson's innovation. On May 11, 1943, the Secretary of the Navy awarded the Nelson Specialty Welding Equipment Corporation the Army-Navy E Award for Excellence in Production. The E Award had been established in July 1942 to honor companies whose manufacturing facilities demonstrated exceptional performance in producing wartime equipment. Both quality and quantity of production were the criteria for the award. Only about 5% of firms involved in war work ever received this recognition. The honor included a pennant for the factory and individual pins for each employee. The ceremony took place at the San Leandro facility, accompanied by full military honors. Navy officers, Army representatives, and local dignitaries attended the event. Factory workers, Nelson's employees who had labored long hours to meet production goals, proudly received their pins. Ted Nelson, standing before his team in his customary work attire, accepted the pennant and delivered a short address. "We did not do this for accolades or recognition. We did this because our nation required it. Every stud we weld, every gun we produce helps ensure that our sailors and soldiers return home safely. That is all the reward we need." The Navy did not stop there in acknowledging Nelson's accomplishments. Facilities that sustained exceptional performance for 6 months after earning the initial E Award were eligible to add a star to their pennant. Nelson's company received its first star in November 1943, followed by a second star in May 1944. By the conclusion of the war, the Nelson Specialty Welding Equipment Corporation had earned 2 E Awards with stars, a distinction achieved by only a select few companies. The citation specifically highlighted the estimated 50 million man-hours saved in naval construction. 50 million hours, consider that for a moment. 50 million hours is roughly equivalent to 5,700 years. If a single individual worked 8 hours each day without pause, it would take over 19,000 years to reach 50 million hours. This massive time savings resulted from a single, straightforward innovation, a spring-loaded welding gun paired with a ceramic flux cap. These efficiencies translated directly into faster ship deployment. More submarines patrolling Japanese convoys. More destroyers escorting vital supply ships. More aircraft carriers launching offensive strikes. More landing vessels delivering Marines to contested beaches. Every ship that reached the water more quickly meant increased combat capability, faster delivery of supplies, and more lives spared. The strategic consequences were immeasurable. Yet Nelson's innovation brought an additional, unforeseen advantage. Stud welding required far less skill than traditional bolting or standard welding techniques. With just minimal instruction, new workers could operate stud welding guns safely and efficiently. This became critical as the war intensified and labor shortages grew. Women entered shipyards in unprecedented numbers. While Rosie the Riveter became the iconic figure representing female shipyard laborers, countless women operated as skilled welders, sometimes referred to as Wendy the Welders. They ran stud welding guns, installed deck planks, and mounted equipment, quickly becoming proficient at these tasks. At its peak, Mare Island Naval Shipyard employed nearly 50,000 workers, including approximately 9,000 women. Kaiser shipyards employed hundreds of thousands, with women making up nearly 30% of the workforce. These new workers needed tools and methods that could be mastered quickly and performed safely. Stud welding met those needs perfectly. By 1944, the momentum of the war had decisively shifted in favor of the Allies. American industrial production overwhelmed the Axis powers. The United States manufactured more ships, planes, tanks, and artillery than Germany and Japan combined. The arsenal of democracy, as President Roosevelt called it, operated at full capacity. Ted Nelson's stud welding guns were a relatively small component of this massive industrial effort, but small components can make an enormous difference. In wartime, efficiency is measured in lives saved and battles won. Faster ship construction meant more naval strength deployed sooner. More naval power resulted in more Japanese shipping destroyed, more islands captured, and increased pressure on enemy forces. The submarine campaign in the Pacific illustrated this impact vividly. American submarines sank over 1,000 Japanese merchant vessels, totaling around 5 million tons, in addition to 1 aircraft carrier, 8 battleships, and numerous cruisers and destroyers. These successes were possible only because the United States produced submarines faster than Japan could destroy them. At the start of the war, Japan had a larger submarine fleet than the United States, but over the course of the war, Japan built only 126 submarines, whereas America produced 203. Every month saved in construction was crucial. Every week a submarine joined the fleet earlier meant another week hunting enemy shipping. The Essex-class aircraft carrier program displayed similar outcomes. The U.S. Navy had only 7 carriers in December 1941. By August 1945, the Navy's inventory had expanded to 99 carriers of all classes. The Essex-class carriers were the backbone of this force. 24 were completed, each capable of carrying up to 90 aircraft. The fast carrier task forces, built around these Essex-class carriers, dominated the Pacific from mid-1943 onward. These vessels bombarded Japanese positions, launched air raids, provided aerial support for amphibious landings, and engaged Japanese naval forces in decisive confrontations. The Battle of the Philippine Sea in June 1944 saw American carrier-based aircraft shoot down more than 600 Japanese planes in what pilots called the Great Marianas Turkey Shoot. This decisive victory was only possible because the United States had more aircraft carriers positioned strategically at the right moment. Faster ship construction allowed for quicker deployment of these vital assets. The D-Day invasion of Normandy on June 6, 1944, required a fleet of 7,000 ships and landing craft. This immense amphibious assault, the largest in history, was achievable only because American and British shipyards were producing landing craft in massive quantities. These vessels were simple, flat-bottomed boats designed to run ashore and unload cargo directly onto beaches. However, they demanded rapid construction and reliable fittings. Stud welding proved perfectly suited to this work. Cargo ramps, davit mounts, and deck fixtures could all be installed quickly and securely. Nelson's technology, originally developed for submarine decks, found widespread application across the entire landing craft fleet. After victory in Europe, WWII in May 1945, focus shifted entirely to the Pacific theater. The planned invasion of Japan, known as Operation Downfall, was scheduled for November 1945. This campaign would require more ships, more landing craft, and more logistical support than any prior operation in history. Shipyards were preparing for a surge in production once again. Then, on August 6 and 9, 1945, atomic bombs were dropped on Hiroshima and Nagasaki, and Japan surrendered. On August 15, 1945, World War II officially ended. The enormous wartime production machine began winding down. Contracts were cancelled, workers laid off, and shipyards either closed or transitioned to peacetime manufacturing. The Nelson Specialty Welding Equipment Corporation suddenly faced an uncertain future. Military orders dried up almost overnight. The company, which had employed over 400 workers at its peak, now confronted the possibility of collapse. However, Ted Nelson had anticipated this moment. During the war, he had been exploring peacetime applications for stud welding. The technology was not limited to ship construction. Any industry that worked with steel structures could benefit from faster, more efficient attachment methods. This included construction, bridges, buildings, tanks, pressure vessels, and automotive manufacturing. The potential applications were vast. Nelson pivoted to civilian markets, promoting his stud welding systems to construction firms, steel fabricators, and industrial manufacturers. The post-war construction boom provided abundant opportunities as America built highways, bridges, skyscrapers, and suburban communities. All required steel fabrication and attachment needs were addressed. By 1948, Nelson's company had successfully shifted to peacetime production. While the business was smaller than during the wartime boom, it was stable and steadily growing. The company continued to innovate, introducing new stud designs, enhanced welding guns, and specialized applications. In 1950, Ted Nelson sold his company to TRW, a large industrial conglomerate. The sale provided Nelson with financial security and allowed him to retire from day-to-day management, but the Nelson name remained on the products. TRW continued to manufacture and market Nelson stud welding equipment, preserving the brand recognition that Nelson had established. Over the following decades, ownership of the company changed several times. In 2000, TRW sold it to Farsantech Incorporated, which was then acquired by Doncasters Group Limited in 2007. In 2018, Stanley Black & Decker purchased the industrial division. Despite all these transitions, the Nelson brand endured. Today, Stanley Engineered Fastening manufactures and sells Nelson stud welding products worldwide. The technology that Ted Nelson pioneered in his Vallejo garage continues to be used globally. Modern stud welding systems are far more advanced than Nelson's original design. Inverter power supplies allow precise arc control, and automated systems handle high-volume production. Robotic welders apply studs in automotive assembly plants, yet the core principle remains unchanged: a stud, a flux cap, a spring-loaded gun, and an electrical arc. 1 second per stud. No scaffolding needed. The applications have expanded far beyond naval shipbuilding. Construction workers now use stud welding to fasten metal decking to steel beams in skyscrapers. Bridge engineers rely on it for guardrail posts and lighting supports. Nuclear power facilities use it for cable trays and equipment mounts. Automotive manufacturers utilize stud welding throughout vehicle bodies for grounding points and trim installation. The technology that Nelson created to solve a naval construction problem now serves nearly every industry that works with steel. Yet the most inspiring legacy of Nelson's invention is seen in the restoration of historic vessels. The battleship Texas, one of only 7 ships to have served in both World Wars, is currently being restored in dry dock. Repairing corroded hull plates and worn fittings requires extensive work, and the restoration team has found that modern Nelson stud welding equipment is ideal for the task. Using this technology, they can attach new steel plates just as Nelson had envisioned 80 years ago. Similarly, the World War II submarine USS Pampanito, now preserved in San Francisco, continues to use Nelson stud welding for ongoing maintenance and preservation. The boat now rests at the Embarcadero, drawing more than 100,000 visitors each year. Preserving the historic vessel and keeping it operational requires constant effort. Nelson's equipment enables the volunteer restoration team to perform welding tasks efficiently without needing certified welders for every job. Ted Nelson lived long enough to see the impact of his inventions extend far beyond what he could have imagined on that day in 1941, when he first sketched his idea in a notebook. He witnessed stud welding become a standard practice in shipbuilding. He saw it adopted across industries worldwide. He observed his name become synonymous with a revolutionary welding process. Nelson passed away in 1994 at the age of 89, having lived to see the end of the Cold War and the dramatic transformation of the world his generation had fought to protect. The statistics of his accomplishments tell only part of the story: 50 million man-hours saved, 2 Army-Navy E awards, thousands of ships constructed faster, billions of studs produced. Yet numbers alone cannot capture the full significance. Behind these figures were sailors who returned home because their submarines were finished in time to join the fleet, Marines who survived because landing craft were ready for their missions, and families spared from devastation because the war ended sooner. The true measure of innovation lies not just in efficiency gains, but in lives preserved. Ted Nelson, the $11 a day welder who was told his idea was impractical, saved more lives than many combat heroes. He accomplished this not with weapons, but with welding, not through destruction, but through construction. The resistance he faced was not unique. History is full of innovators dismissed by authorities. Wilbur and Orville Wright were told powered flight was impossible. Henry Ford was mocked for proposing mass-produced automobiles. Chester Carlson spent years trying to sell his xerography process before finding a buyer. What set Nelson apart was his refusal to accept rejection. He did not argue endlessly with bureaucrats. He did not waste time trying to persuade skeptics. He simply quit his job, risked his savings, and proved his concept worked. Then the market validated his invention. This embodies the essence of American innovation: not waiting for approval, not adhering blindly to established protocols, not accepting that things must always be done the same way. It is about identifying a problem, developing a solution, and having the courage to implement it despite institutional resistance. Mare Island Naval Shipyard, where Nelson had worked and where his idea was initially dismissed, closed in 1996 after 142 years of service. Throughout its history, the yard built 512 ships and repaired thousands more. It was responsible for constructing 44 submarines, including the last nuclear submarine built in California, the USS Drum, launched in 1970. The base was recognized as a California Historical Landmark in 1960, and portions of the site were designated a National Historic Landmark District in 1975. Today, the former shipyard is being transformed into a commercial and residential area. Several of the historic buildings remain, including the chapel, dry docks, and industrial facilities. Walking through these preserved structures, visitors can envision the frenetic activity of the wartime years, when tens of thousands of workers labored around the clock building submarines. In Building 46, the former pike shop that remained operational until 1984, there is now a small museum. Exhibits include tools, photographs, and artifacts documenting the shipyard's history. However, there is no dedicated display honoring Ted Nelson. There is no monument recognizing the welder who saved an estimated 50 million man-hours. His story is largely forgotten, remembered only by welding professionals and maritime historians. This lack of public recognition likely would not have concerned Nelson. He sought neither fame nor accolades. He was focused on solving a problem, improving processes, and contributing to his country's war effort. The fact that his solution worked, saved both time and lives, and transformed an industry was reward enough. Yet his story holds a valuable lesson for every generation. Innovation often emerges from unexpected sources, not from credentialed experts, but from workers who encounter problems daily and know how to solve them. Not from corporate research laboratories, but from garage workshops where tinkerers experiment until they find practical solutions. Not through formal channels, but from individuals willing to risk everything on an idea they know is correct. The next transformative innovation could come from a shipyard welder, a garage mechanic, a hospital nurse, or a classroom teacher. It might emerge from someone official channels dismiss as unqualified, someone bureaucrats instruct to follow rigid procedures, or someone experts deem wasting time on an impossible problem. History teaches that these voices deserve attention, not because every idea will succeed, but because the rare successful idea can change everything. Ted Nelson's ceramic flux cap was a small piece of ceramic, and his welding gun was a simple spring-loaded tool. Yet together, they eliminated scaffolding, saved enormous amounts of time, improved safety, enhanced quality, and accelerated ship production at a critical point in history. 50 million man-hours, equivalent to approximately 5,700 years of labor, were saved by a single welder's initially rejected idea. And these numbers represent only the direct construction time savings. They do not account for the strategic advantages of faster ship deployment, the lives saved because submarines reached the Pacific sooner, the morale boost of surpassing production goals, or the deterrent effect of American naval power growing faster than enemies expected. The full significance of Ted Nelson's invention may never be completely measured, but it is certain that America's victory in World War II depended as much on industrial ingenuity as it did on military courage. The battles were fought and won by soldiers, sailors, and Marines. Yet the ultimate victory in the war was secured by workers, engineers, and innovators. People like Ted Nelson, who identified a problem and created a solution. People who would not accept inefficiency when efficiency was achievable. People who understood that in a total war, every minute saved in production meant lives saved on the battlefield. As we confront the challenges of the 21st century, this lesson remains crucial. The issues we face, climate change, dwindling resources, aging infrastructure, demand innovation at every level. Solutions will emerge not only from prestigious universities or corporate research labs but also from everyday workers who recognize problems firsthand and devise practical solutions. The next Ted Nelson could be inventing a more efficient solar panel in a small garage workshop. The next breakthrough might arise from a factory employee who knows exactly where time and energy are being wasted. The next leap in efficiency may come from someone whom official channels have already labeled unqualified. We must pay attention. We must encourage innovation from every source. We must eliminate obstacles that separate problem identification from solution implementation. History reminds us that some of the most significant innovations originated from individuals outside the established system simply because the system refused to listen. Ted Nelson began as an $11 a day welder. He ended his career as a wealthy industrialist whose technology saved his nation. Yet he never forgot his beginnings. He never adopted airs or pretended to be anything more than a mechanic who saw a problem and solved it. In his later years, when asked about his accomplishments, he would simply shrug and say, "I just made a better mousetrap. The world came to my door." It was not genius, it was plain common sense. But common sense applied at the right moment, with courage and persistence, can change the course of history. That is the essence of Ted Nelson's legacy. It is not measured in the 50 million man-hours saved, nor in the 2 Army-Navy E awards, nor in the global company that continues to bear his name. His true legacy is proof that a single individual, armed with a good idea and the determination to act, can make a tangible difference. That legacy endures every time a welder activates a stud welding gun, every time a ship is built faster than traditional methods allowed, every time someone examines an inefficient process and asks, "There has to be a better way." Ted Nelson posed that very question in 1941, and his solution helped win a war. What questions are you asking today? More importantly, when experts insist it cannot be done, when bureaucrats insist you follow protocol, when skeptics dismiss your ideas, will you have the resolve to prove them wrong? The history of innovation shows that, at times, the most important action is to disregard the experts, trust your own observations, and construct the solution you know will succeed. Ted Nelson did exactly that. 80 years later, welders across the globe continue to use his invention every single day. And somewhere, perhaps in a garage or workshop, the next Ted Nelson is sketching an idea everyone believes will fail. They will be wrong because the most transformative innovations do not arise from following established procedures, they emerge from people who identify a problem, know how to solve it, and refuse to accept no as an answer.